Welcome to Paul. It's my great pleasure to introduce Eli Putterman from Tel Aviv University, who's going to tell us about curvature of graphs.
Thank you, Tomasz. Thank you, Kasha, for inviting me and everyone for showing up. So what are we going to talk about today? So I will talk about a general framework for dealing with Laplacians on different kinds of spaces and using and proving functional equalities, which is called gamma calculus, which is something that is proven is most easily carried through on continuous spaces, things like Rn certainly, but also manifolds. And it is not at all trivial how to make this kind of framework work for graphs. So I will present a very particular way of making this work in the second part. But there are many such ways, and I'm not even going to mention other ways because it's really very active. And as an application, to convince you that the definition I will propose has some utility, I will show how one uses it to prove a result on spectra of certain densities, which is similar to a result I proved with Klautag last year, and that will be it. Okay, so let's start with the Poincare inequality. So I will remind you that, like, the original Poincare inequality basically allows you to bound, given a function with zero mean, it allows you to bound the total integral of f squared by some kind of energy, right? The integral of its squared gradient, or the gradient. If you should think of it as some kind of energy density, as how much the function is changing at any given point. And there is a constant here. The constant here depends on your domain, and the study of these Poincare constants is, a huge part of geometric functional analysis. And these constants are very, very closely connected to the geometry of the object under study. So the constant is just like 1 over the spectral gap, the smallest non-zero eigenvalue. And a theorem from over 60 years ago states that if your domain is convex, then you have a very tight connection between the Poincare constant and the geometry. As in, if you have a convex domain which is pretty small, then in terms of its diameter, then the Poincare constant is bounded in terms of that squared, and the squared is the correct degree of homogeneity in terms of the length, as one easily checks. And so in general, when we say that a manifold or any kind of space really satisfies a Poincare constant, we simply mean that the variance is bounded by some kind of by a constant times an energy density, where it's usually it's easy enough to say what this squared gradient is on a Riemannian manifold. It might not be so easy to say what it is in the general case. Okay, so now I'm going to start talking about gamma calculus. So what happens in the Poincare inequality? In the Poincare inequality, you have a measure space. It's a finite measure space for a bounded domain. And you have a notion of energy density. And the energy density is related to, by integration by parts, to a differential operator, which we all know and love, the Laplacian, which we know to be very important for all kinds of reasons. And something which is not obvious in, it doesn't show up explicitly in the statement of the Poincare inequality, but shows up in many, many other places, is that we have a heat semigroup. The heat semigroup is basically the exponential of the Laplacian, the negative Laplacian, depending on your definition. The point is it's all of its if you take delta such that all of its eigenvalues are negative except on constants, then then you look, then formally what it means is what happens is that PT causes all the components of your function to decay exponentially except the constant component of your function. So it dissipates energy. And basically what we want to do is to take these intuitions and apply them in as general as possible a context, while having basically the same operators and the same formalism. So you start with a measure space, and you actually start with a semigroup of contraction operators that preserve the measure. And under very general conditions, you have the semigroup has a generator, and then one can write the semigroup as the exponential of the generator. And some technical conditions, almost always satisfied in interesting cases, is that we want it to be self-adjoint. We want it to be ergodic, which means that essentially it means that, well, if you think about a probabilistic kind of thing, if you think about a semigroup as basically telling you what happens to a function under evolution via a random walk on your space, then ergodicity means that eventually you'll cover the whole space by this random walk, which for example doesn't happen when you have two disconnected domains, and then heat flow on the union of these domains will equilibrate each domain to have to a constant function on each domain, but different constants. But in general, but if we have like a connected domain, then it equilibrates to a single constant function, which means that that pointwise the semigroup applied to a function converges to the integral of the function, and that's going to be the standing assumption. And yeah, okay, so for those who are familiar with the stochastic stuff, then the standard example is the law of an Ito diffusion process, and then you have a second order differential operator, but this is not always going to be the case. Okay, so we have L, which is our Laplacian, our generator, and then we want to define an energy density. So we don't do it a priori via integration by parts. We do it pointwise by this kind of we try to pick out like some kind of mixed term of what happens when you apply the Laplacian to a product. Then you get the Laplacian applied to each of the factors plus some kind of mixed term. This mixed term is going to be our gamma. And in the simplest example, it's just the product of the gradients. And okay, so some properties of this gamma are, first we have that the integral of L for any function is 0, and if we and that implies that if we integrate gamma, then we have an integration by parts formula, just as we saw in the original setting of omega being some domain in Euclidean space. What else? Yeah, so gamma 2 is basically obtained by applying the same mixed term process with gamma in place of the product of two functions. And okay, this is really the first thing, which is unmotivated. Like we don't really, it's not obvious what this thing is related to in terms of our elementary examples. We can see that by integration by parts, then the integral of gamma 2 is going to be the same as the integral of L squared, essentially. But it's still not clear what this means pointwise. So let's look at some examples, and then we'll see what this quantity is aiming to actually capture. So if you have a Riemannian manifold with a metric G, this volume measure, L the usual Laplace-Beltrami operator on the manifold, then gamma, the energy density, the Carré Duchamp, is what you expect it to be. It's the the squared gradient, where, you know, squared gradient it's measured according to the metric. And gamma 2 is something kind of very general. It's the squared Hilbert-Schmidt norm of the Hessian, plus another term, plus the Ricci curvature, which is a second order tensor applied to your gradient. So this second term is really where the geometry of your manifold sets in. To look at a different example, if we have smooth positive density on Rn, which we write as e to the minus w, then we start from gamma. We start from wanting the energy density to be the same as when you don't have any measure. So we take the gamma to still be the squared gradient. And then that forces us to choose L in a certain way. If we want an integration by parts formula to be satisfied, then L has it has two terms. One is the Laplacian, same as in the unweighted case, and one is a term which depends on your density. And then the gamma 2 also has two terms. One is this generic squared norm of the squared Hilbert-Schmidt norm of the Hessian, and the other is the Hessian of the logarithm, or the Hessian of the negative logarithm of your density applied to the gradient. So we have, like, again, a second order term which is very generic, and a first order term which depends on the geometry in your specific context. And these are continuous examples, but we can also do a discrete example. On graphs, you have a very natural notion of Laplacian, which I'm not going to write down here, but I write down slightly later, in which case, when it computes explicitly that gamma, the energy density, is exactly what you'd expect. At each point, it's you sum over the difference between yourself and neighboring points, square that, and that's your energy. Unfortunately, gamma 2 is kind of a mess in that case. And okay, so much for the formalism. And now we have this curvature condition. We already saw that gamma 2 captures something about the geometry. So to placing conditions on certain, like, very elementary point-wise conditions that we can place on gamma 2 are supposed to be telling us something about the geometry. And the curvature condition is just defined as the basically a point-wise bound we want on the value of gamma by the value of gamma 2. We'll see, why it's called the curvature condition and what this means exactly in just a second. We can generalize it to have another term, and this is called the curvature dimension condition. And then things get even more complicated. But the point of this condition is that you have this kind of very generic condition, and you hope that using this generic condition and then the algebra of gamma 2, L, PT, and everything else, one can prove functional inequalities or some other properties which interest us while being totally agnostic to the setting. It's sufficient just to have this condition and to use the algebra. So that's why it's a formalism. It's a framework. Okay, and I had an example here, but I don't think we have time to do the example, but I will. The example is of how you use gamma calculus to actually prove something, but I will give examples of what the curvature condition actually means. So remember that we have gamma 2 is the for a Riemannian manifold is the squared Hessian, the squared Hilbert-Schmidt norm of the Hessian plus the Ricci curvature applied to the gradient. Now, now, if you think of the sphere, then the sphere is something which has constant Ricci curvature. It's just the identity times 1 over r squared, where r is the radius of the sphere. So one sees immediately that the sphere satisfies the curvature condition with constant 1 over r squared. This is, the motivating example. This is why we call it the curvature condition, because what on a Riemannian manifold, the term you're going to use to prove that gamma 2 is bounded below by some constant times gamma is precisely this Ricci curvature term, which involves the first derivatives, while the second derivative term in gamma 2 can't really be used to bound gamma. But the point of gamma calculus is that we have curvature also in settings which are not Riemannian manifolds. So if we look at the other example we said before, which is Rn with a density, specifically we'll take it to be log-concave, meaning that it's e to the minus w with w a convex function. Then gamma 2 is, well, at the very least, we can say that it's always positive because the Hessian of w is positive. And in general, slightly more generally, if w is what's called the strongly log-concave, if mu is strongly log-concave, which means that w is k convex or something, I'm not exactly sure what the terminology is, but the point is that its Hessian is bounded below, motivating example, the Gaussian, in which you have equality here, then your space satisfies the curvature condition with a positive constant. So this is basically saying that Rn with the Gaussian is somehow analogous to a sphere. They're both positively curved spaces. Okay. And just as I said, the point, this gamma calculus allows you to prove lots of interesting things about your spaces, Poincare inequalities, log Sobolev inequalities, all kinds of stuff. And also certain equivalences, which you can't really call them functional inequalities, but they're such as exponential concentration or whatever, that are also come out of this gamma calculus. Another place where gamma calculus shows up, and I haven't updated the slide, so I should have put in more recent references, but in stochastic localization, admittedly, that's not the main thing that happens, but one does use certain, one way to think about it is to decompose a log-concave measure into pieces, all of which satisfy curvature dimension condition, and then you can use that to prove things about the measure. Okay, so that is about gamma calculus in general. And now I want to talk about gamma calculus on, that's all background. Now I want to talk about gamma calculus on weighted graphs. This is where this starts to be new stuff. So on a graph, we have like the definition of the graph Laplacian that absolutely everyone uses, which up to maybe a normalization if the graph is deregular or something, you simply it looks actually like a first derivative, not like a second derivative somehow, in that you sum over the difference between you and each of your neighbors. And one checks that gamma f is going to be the energy density, which is just a very, very obvious discretization of what happens in the continuous case, squared sum over squared discrete derivatives. And then we want to generalize this to what happens if we have a graph with a measure. I don't want to say a weighted graph, because a weighted graph usually you place weights on the edges, and then you should do something different. But a graph with a measure is something which we think of as analogous to Rn with a density at each point. So you want to place a density on the vertices, not on the edges. And so note, so we're going to work by analogy. So as I said before, for the Laplacian does seem to be analogous to discrete derivatives, and in particular, if you take g to be z or z to be n for that matter, but certainly in the case of z, then the Laplacian of a function on z looks just like a discrete second derivative. So a discretization of the Laplacian, i.e. the second derivative on the real line. So we would expect this analogy to continue to hold for a weighted graph, or specifically, again, working with a specific example, working with z. So in which case we have our second derivative term, and we have another first derivative term, which is exactly the derivative of the logarithm of rho. And in that case, your energy density still stays the same. And remember that we obtained L rho by starting from the condition that the energy density is the same, and then looking at what L rho needs to be in order that we have an integration by parts formula. So we can do the same thing on G, on any graph G. And then one determines that the definition which one needs in order to get this integration by parts formula is to, again, have a Laplacian plus another term, which is, if this were a continuous setting, it would be, derivative of log rho dot product with derivative of f. But in the discrete setting, the derivative of log rho is not exactly the same thing as 1 over rho times the derivative of rho. But it's essentially the same thing. There are problems. It turns out that if you take this to be L rho, then it is not true that gamma of f and g is L rho fg minus f L rho g minus g L rho f. But it is a term, but this difference is a term which integrates to 0. But this does seem to be a very natural thing that one should at least see if it works. Okay, so let's work with the simplest possible example where we have, a reasonably simple structure and also a very strong analogy to a continuous case, namely z. So on z we have a notion of log concave density, which is very simple. We can take there's no problem to define a notion of convexity for a function on z. So if log rho is concave, it's exactly the same thing as if it's a local condition. It's that it's what I wrote here. And if our definition of L rho is the right definition, then log concave densities on Z should have the same properties as log concave densities on R. They should satisfy a curvature dimension condition. So a pointwise positivity property of gamma 2. And in fact, this is true. We do have this theorem. It looks a bit scary, but I'll walk you through it. So AX is what I call the log concavity deficit, right? It's how log concave you are at a given point. So first of all, the first statement is quite easy to digest. It just says that if you're log concave, then indeed the Laplacian on Z equipped with the measure rho satisfies the curvature dimension condition with constant 0, which is exactly the same thing as an arbitrary log concave density satisfies on R. It gets complicated if you want to satisfy a curvature dimension condition with constant K. It's not that simple. The really simple thing one would want is that if AX over rho x squared to get some kind of homogeneity is greater than K, then you get CDK infinity. That's not the case. But something like that is the case. The problem is that instead of, AX and rho x at each point, you have AX and rho x at slightly different points translated. Now, if you think of a continuous density that you sample on the discrete grids which are finer and finer, then these things each of these terms will go to just the second derivative of the log of rho at your point x. So this is in some sense a generalization of what happens on R. It's just, a bit computationally annoying. And the reason that it's a bit computationally annoying is that one has to deal with quadratic forms. Specifically, one wants to show that the quadratic form, which associated to gamma 2 is bounded below by k. This shouldn't be f. I'm sorry. This is a mistake. It's k gamma f at x, not gamma 2f. And again, because discrete derivatives are annoying, they don't satisfy product rules, they don't satisfy chain rules, then one gets all these values at close points, and involved in this quadratic form, and it's a matrix that one has to prove by hand that is positive definite. Okay, so this is pretty encouraging. It says that.
Sorry. Could I ask, in your definition of log-concave discrete density, do you allow internal zeros? Like 1, 0, 1 less? No. So it says the support is a continuous interval and 0 outside, right?
Yeah.
Well, is it true without?
What'll happen is that if you have internal zeros, then everything I'm thinking about, which is random walks associated to these things and Laplacians, then if it's disconnected, then it'll be exactly like disconnected things on R. That everything will happen within each domain, and they won't really talk to each other. So then you won't have like Poincare inequalities and stuff. It'll be for silly reasons. So it's not really a big deal. But yeah, for simplicity, we don't have internal zeros. We just have like one continuous interval. Good question. Okay, any other questions? Okay. So that was pretty encouraging that we have this this discrete gamma calculus, which gives us a notion of a log-concave density, which is at the very least implied by the elementary notion of log-concave density. And what I didn't say, let me go back, is that CDK infinity implies that a Poincare constant with a Poincare inequality with constant 1 over k holds. So this means that such log-concave measures do satisfy Poincare inequalities. Unfortunately, for log Sobolev and other such inequalities, then you have chain rule and such issues which make it harder. But at the very least, we do have that for strongly log-concave measures on Z, i.e. those which satisfy this inequality with some k, then they satisfy at least a Poincare inequality that just follows immediately by the formalism. Okay, but we would like to also have some more interesting applications. So I chose to show you one application that we can do, which is this spectral monotonicity result. So let us switch gears for a second and go back to Rn. Now I'm just going over like a previous result from last year with Klartag. So we have a log-concave density rho on Rn, and then we apply heat flow to it, right? We can involve it with the Gaussian. So it gets wider, it spreads out. And if you remember the very first slide when we talked about Payne-Weinberger and the bound on the Poincare constant, then one should have the intuition that the more spread out a measure is, the larger its Poincare constant is, and that means the harder it is to bound its integral or its squared integral by the integral of its energy density. So we would expect that convolving a measure with a Gaussian, i.e. spreading it out, is something which is going to make its Poincare constant bigger. And one point which is very important to make at this point is that convolution preserves log-concavity. If we have two log-concave densities, then their convolution is log-concavity. In particular, convolving with the Gaussian preserves log-concavity for all t. And that actually allows us to prove this theorem, which is which verifies this intuition, which is that the Poincare constant of a density of a log-concave density increases when you apply heat flow to it, when you spread it out by convolution with the Gaussian. And in fact, one has a stronger, more local statement. So note that the Poincare constant is just 1 over the spectral gap, 1 over the smallest possible Rayleigh quotient of a function which is orthogonal to the constants. And one actually shows that one can one has a transformation on functions starting from L2 rho and going to L2 rho t, which I call PT star, which I'm not going to talk about at all today. A transformation on functions such that you take any particular function L2 rho, and then you apply this transformation. You get a function in L2 rho t, and the Rayleigh quotient of this is no larger than the Rayleigh quotient of the original function, which precisely means that the eigenvalues essentially are decreasing, at least if you have a discrete spectrum, and that the Poincare constant, which is 1 over the smallest eigenvalue, if there is such an eigenvalue, is therefore increasing. So we would want to do this in the discrete setting. Okay, so we are, at the outset, we're going to look only at semigroups on Z, which are log-concavity preserving, like the heat flow on Rn. But the heat flow on Rn is more than just, well, it's actually the only Markov semigroup which preserves log-concavity. It's also up to rescaling time and up to normal, up to including a deterministic drift. It's the unique Markov semigroup, which is translation invariant, which doesn't really, which, so we want to consider on Z Markov semigroups which are translation invariant, i.e. which work by convolution. And on Z, unlike in Rn, you have a ton of convolution semigroups. To get a convolution semigroup is basically the same thing as a continuous time random walk. What does that mean? I'm at time t, I wait for an exponential amount of time, and then I jump exponential amount of time, by which I mean like exponential random variable. I wait an amount of time specified by an exponential random variable, and then I jump where the place to which I jump is, or the amount, better to say, the amount by which I jump is specified by a probability distribution on Z, which I'll call the generator of the convolution semigroup. And each generator of a convolution semigroup gives you a different thing, which is reasonable to, which is a convolution semigroup, unlike on Rn, where you have very few. But which of these convolution semigroups actually preserve log-concavity, which we will need? And the answer is that the family is not particularly rich, but it's still somewhat interesting. That if you have a continuous time random walk on Z, then, and you look at the associated convolution semigroup, then you preserve log-concavity precisely when you can only jump by at most one step to the right or one step to the left at each time step. And this is actually pretty cute. So, and the proof is not difficult. So I think I will try to give it. So first of all, why is this? Let us do necessity. Meaning if you can jump by more than one step at a given time, why is PT not going to ever be log-concave? So at small time PT, at small time, you're only ever going to jump by approximately, we can write PT as delta 0 minus plus, excuse me, TL, where L is our generator, L is our probability distribution on Z, and delta 0 is just a Dirac mass at delta 0. So if we have our original L, which let's say it's a lazy random walk, so it has something at 0, it has something at 1 and -1, and let's say it also has something maybe even pretty small at 2. So I claim that PT is not going to be log concave for t small enough, and the reason being is that when you look at this for really small t, then the picture will look like this: 0, something very large, but most of the time you're not going to jump at all, and then small things here and here, and then another small thing here. But the point is, the condition we want to happen is that rho of 1 squared is greater than rho of 0, or rho t, let's say rho t 0, rho t of 2. And this is not going to happen for small enough t, because rho t of 1 is of order t, and so this is the left-hand side is of order t squared. The right-hand side is of order t. So this is not going to be the case for small enough t. On the other hand, and let me erase this quickly. On the other hand, we want to prove the other side. Sorry. The other side is even simpler, I guess. On the other hand, we can, this should be approximately, sorry, the actual expression for PT is an exponential, of course, t delta 0 minus t delta 0 minus L equals the limit as n goes to infinity of delta 0 plus t over n delta 0. I'm sorry. No. Like the zoom bar is conflicting with the annotation bar. How do I hide floating medium controls? Okay. L minus delta 0 to the power n, right? The same exact formula as for the exponential of a number. And okay, so again, if you're supported on -1, 0, 1, then for small enough n, the picture is that you have one big, then this thing looks like one big thing at 0 and smaller things at 1 and -1, and that's of course log concave. And since log concavity is preserved under convolution, then convolving this thing with itself to the power n is still log concave. And finally, the limit of log concave things is log concave. So in fact, you get that PT preserves log concavity. That was the proof. I hope it was comprehensible. Okay. And finally, sorry. Yeah. Okay. So finally, we do get once we've identified which semigroups on Z preserve log concavity, then we can ask if in fact we still have this spectral monotonicity result for such semigroups, and indeed we do. the Poincare constant increases, the eigenvalues decrease if there is a discrete spectrum. The proof is not much fun. There's a dynamic semigroup technique. Yeah, so if you look at the bottom here, there's a dynamic semigroup technique, which means like a way to associate with each function in the original L2 space, a function in the L2 space of row T, and one shows that the Rayleigh quotient decreases. It decreases in the exact same way, but again, due to annoying properties or annoying failures of properties one would want to have in the discrete case, then it's not as clean as showing that the Rayleigh quotient decreases for the semigroup and Rn, but one can nonetheless do it, and then one gets this discrete spectral monotonicity result. And that's all I have to say. Are there any questions?
Thank you, Eli. Thanks a lot for the talk. Yep. How about some questions, please? Okay, maybe I was just curious, this curvature condition, no, what is it called? The CD of K condition that you derived in your main theorem. Are there some natural examples of measures, discrete measures? I mean, densities for which you
Yeah, like what you would think, meaning like a discrete Gaussian kind of thing does satisfy this for, I don't know, K plus O of something, which, not very.
So then binomial as well, or these kind of things?
Yeah, I actually didn't specifically check the binomial, but yeah, maybe it actually turns out to be simpler for binomial distributions. But yeah, I mean, a binomial is an approximation to a Gaussian, so it should happen. Like, I don't know, the least I would want to bet is that I wouldn't want to bet on if a binomial is going to try to approximate a Gaussian of variance T, then I wouldn't say you get exactly 1 over T, but at least order of 1 over T or something. Maybe even like 1 over T plus some discretization error.